Hey there, everyone. In today's teaching lesson, I'm going to be talking about SQL. Pretty much without exception, all of my demos and videos and instructional sessions have been related to Python and all the things you can do with Python, all the automation, optimization, classification, what else? Regression, clustering, deep learning, machine learning, all kinds of data science topics. I covered lots and lots of things. This one's going to be a little bit different. I think it's relevant only because SQL is so ubiquitous. You will never get away from it. It's been around, I think, now close to 30 years, at least 25 years ago, SQL came on the scene, and it's really dominated ever since. So I think any data scientist or machine learning engineer should have at least basic, probably basic to intermediate, and maybe even advanced SQL skills in their toolbox. It's a nice tool to have. And even business analysts, project managers, executives probably know some SQL too, right? So it's not just for technical people. It's pretty much unanimous and extremely ubiquitous for all kinds of people in the business world and even not in the business world, just all over the place, right? SQL is everywhere. We'll never get away from it. So what is SQL? It's a structured query language used for managing and manipulating relational databases. Okay, this is a declarative language, meaning that you specify what you want to achieve and you don't necessarily say how it's going to be done, but the query tool will do the job for you, right? And it'll actually optimize how the code is run and managed. So you just have to understand the objective. What do you want at the end after the code runs? And SQL, the SQL optimizer will actually do the whole lift for you. This is different from a procedural language like Python, where you create functions, although you can create functions in SQL too. But in Python, it's more procedural, where you describe all the steps that need to happen to get something done. With SQL, there's really no steps. You just describe the outcome, and the query optimizer will handle the steps. So that's the difference there. There's three basic types of SQL. The DDL, data definition layer, that's used to define and manage the structure of the database, including creating, altering, defining tables, any constraints like this, things like this, right? Data manipulation language, this is for inserting, updating, deleting records, and selecting. Now, most of the SQL that you write will probably be DML, data manipulation language, but DDL is important too, right? If you want to create tables and alter tables, that's how you do it, right? I mean, you can click on SQL Server and create those tables just by clicking on the menu, right? But DDL is really a better way to do that. It gives you a lot more control, and it's a lot more flexible too. DQL is data query language, and that's where you will run select statements. Most of the SQL is probably going to be select statements, and if you have write authorization, then it could be deleting, inserting, updating, upserting, which is an update and an insert at the same time. Kind of, it basically makes an update if the record exists and is a newer record that needs to be overwritten. That one gets overwritten. If the record doesn't exist, it inserts the record. So we've got that too. And then overall, SQL is just a powerful tool for interacting with relational databases, right? We have relational databases where standard ANSI SQL dominates, and nowadays we actually have NoSQL databases where you can insert XML files, JSON files, and so on and so forth. Right? It's not structured and has nothing to do with querying. Although, I mean, you can still query. Sorry, you can still query the database. It's just not only SQL; it's SQL plus NoSQL, right? Not only SQL is what that means. So here's the different types of joins in SQL. You have a left join where you'll take all of the items from the left table and only the matches on the right table. An inner join will only take the matches between the left and the right. The right outer join will take all the records in the right table and only the matching records on the joining table, right? And then you have a full outer join, right, where you'll take everything from everything, and you could have a full outer join with an exception where the keys are null, where the matches are null between the two tables that you're joining on. Okay, so those are the basic types of joins. So let's look at an example here. We have create table. That's going to create the table and then the department name. And if I go over here, that is actually DDL, right? We're creating a table or altering the table. So DDL is the first type of SQL statement that we'll see here. And there's more DDL over here, drop table, right? So if the table exists, drop it. And you can even write a condition. If table exists, drop it. If it doesn't exist, then it just does nothing, right? So create employees, there's more DDL, right? So we're creating an employee and making an insert into, okay, so you have to have write authorization for this. If you only have read writes, it's called. If you can only read the database, you can only do selects. If you have admin privileges, then you can insert into. So hopefully we have admin privileges. We're going to be inserting into this database, HR, engineering, sales operations, sales and trading, right? And then insert into another table. That first one was departments and employees. Now we are going to do a select to join these two tables together. So we're going to select employees, right? And departments dot department from employees. There's the table, right? Inner join, we're looking for the matches between these. Departments on employees, that is the name of the table, and this is the ID field in the table. On employees ID, employees dot employment ID equals department dot department ID, and then we'll see the matches right there. Okay, so pretty cool, pretty straightforward. Now we have a left join. So that was an inner join. If you look here closely, we have an inner join, so we're looking at the matches between those two tables, right? A left join will take everything from the left table, and the left table is the one that comes first, right? So employees comes first, and we are doing a left join right here. Here's the left condition where employee dot employee ID equals department dot department ID, and we have everything from employees, right, and only the matches from department, right? So all the employees show up because employees comes first. It comes before the left statement, so we get everything from that table, and then only the matches on the right table, which is departments, right? Okay, so here we'll see the opposite. Now this is right join to get everything from departments because departments come first before the right statement here. Whoops. Right here, right is right. And then everything from employees if the employee matches. In this case, it does. Okay. So a full outer join. The table actually doesn't matter. You can pull all the positions from all the tables. All the left rights don't matter. A full outer join will take everything, right? So select, just like we saw before, full outer join. So there's no left, there's no right, there's no inner. This is getting everything under the sun. Full outer join. Okay, on departments equals department. And let's see what it looks like. Yeah, we got all the departments, and there happens to be some blanks, so we have some nulls from the employee table, right? Because we have more data in the department table. Okay, so Cartesian product. Now this is a combination of everything, and this isn't even a join. It's just taking everything from all the tables. Now in practice, you don't really do this. I don't think I've ever done this, to tell you the truth. But there are cases where you might want to see every possible combination of everything. If you were trying to look at, I suppose, potential winning lotto numbers, and you want to see every possible combination, our Cartesian product would show you that. If you wanted to schedule a bunch of baseball teams to play every other baseball team in the league, Cartesian product would do that for you, right? It shows you every possible combination for every matchup of the baseball teams, every combination of those lotto numbers. But again, in real life, you don't really use these too much, but I guess it's nice to have and need it, right? Full outer join versus a Cartesian product. So both joins result in the left outer join and right outer join being all inclusive, right? It takes everything from both tables, matching rows, and filling any non-matching value as a null, right? You can't have nothing returned. You have to have a null, which could be nothing, but you can't just have like a blank there. So it's going to match all the possible combinations, and anything that doesn't have a record, it's going to show as a null. A Cartesian product will combine everything from every row in the first table with every row from the second table, right? So again, it's all of the potential combinations from those two tables, right? Now, a cross apply is used to do table value function for each row by the outer table, and it's usually used if you want to apply a function to each row. So again, like I said before, you can create functions in SQL Server and save the function and call that if SQL doesn't do what you want it to do, right? If you have a custom job or some kind of custom process, you can create a UDF, user-defined function, and use cross-apply to evaluate every row in one specific table, right? If that's the ask. This isn't used too often, but there are cases for that, right? Sometimes if you have custom subqueries, which is a query within a query, you might need to do that. I'll show you an example of that a little bit later. Cross-apply and inner join involve matching rows based on conditions, right? Their usage and behavior can be different. Inner joins are standard ways to combine matches between two tables, but cross-apply is really used as a table evaluator. So it scans every single row in a table based on the outer table expression, okay? Should be aware of that. So let's look at another example here. If we have tables, we'll drop it. This is commented out. The two hyphens next to each other is a comment in SQL Server. So let's create, drop the tables if they exist and create new tables. We have employees, and we are inserting data into employees. You have the name, and then I guess, department ID, yeah. And then we have departments, and then we have department ID and department name. Okay, so the department IDs will match up. Here's a cross-apply, select star from employees cross-apply, and then we have the subquery, select departments, department name, where employee dot department ID equals department dot employee, dot department ID as department details. So the as clause here indicates that we have an alias. Okay, so we're doing this select query, the select subquery, selecting all the matches between these two tables, and running a cross-apply to get the results from that. This is an alias. Sometimes it's called a temp table because this is temporarily creating a table only when the query runs, but we don't really have a table in the database, right? So that's a temp table that's used as a placeholder to show the results of the query, but there's no table saved as a result of running that, right? Now we have an outer apply. Again, subquery right here. Select from where employees dot department ID equals department dot department ID as department details. So another alias, right? And we are doing an outer apply. So now the cross apply is basically running like an inner join over here. That's what that does. But the outer apply is actually running like a left join. Okay, so you can see all the records from the employees, but only the matching department IDs. And if there's no match, because David doesn't have a match. Let's go up and see why David doesn't. Or employee ID number 4. I think there's just 3. That's why. Okay, let's go up and see what's going on with David. Oh yeah, he's just null. So there's nothing to match, right? We have 101, 102, 103. I guess if David had the 103 over here, then he would come through, right? But since that's null, we don't have the department ID. It looks like a mistake, possibly, or maybe he's a new person and hasn't been assigned to a department yet. I'm not sure, but that's why the outer apply is showing the nulls, right? Because it's pulling back everything. But the cross apply is functioning more like an inner join, right? So that's what we see in notes down here. Outer apply returns all rows from the left table. So that is like a left join. That's exactly what we said. And the cross apply is functioning more like an inner join there. Okay. So let us continue on. We have a few more examples to work through here. We are creating a new table, orders, with order ID, customer ID, and amount ordered, and you'll see all of that down here. We're inserting the data. Very nice. Okay. Now let's use the case when. This is used when we have to categorize orders into groups or buckets. So we can use a case when a certain condition less than 1,000, we will call that low, greater than or equal to 1,000, but less than 5,000, this is going to be medium, and orders greater than 5,000, we're going to call that high. Those are high order items, high net worth people, high valued clients, something like that, right? So we're assigning a identifier or label or bucketing these items when the order amount falls into these different categories. We have low, medium, and high, right? So there's a different way to represent your data, to transform your data into a different shape and form if that if that suits you. Okay, so now we have a case of max case when. So similar to what we saw with the when, very similar. We have when combined with the max condition. Okay, so when max order less than 1,000, low spender, max order greater than or equal to 1,000 but less than 5,000, medium spender, and greater than 5,000, high spender. Similar, but we're using max when instead of just a when. And whoops, kind of skipped over it there, but you can see the results. Okay, max case when, very nice. Okay, now let's create another table. This is a customers table, inserting data, and then we have an orders table. So you see this a lot. I mean, in generic examples, customers and orders, and you have all the details here. So we have non-correlated subqueries and correlated subqueries. So if you have two tables and orders and customers, you want to find customers who have placed orders with amounts greater than an average order amount, you need a correlated subquery. Okay, so in this example, the select average over or average order amount from orders is a non-correlated subquery because it doesn't reference the columns from the outer query. Okay, so if you're referencing columns in the outer query, it's going to be correlated, and you need that outer query to run. A non-correlated subquery can run all by itself, right? It can run as part of a subquery or independent of the subquery. A correlated subquery has to have that column that you're referencing, or it can't run, right? So if you cut out the subquery, that will run all by itself. A correlated subquery will not. It needs that outer column as a reference to be able to run the logic that you tell it to run. So let's look at an example, non-correlated subquery. You have the subquery right here, select order ID from orders where order amount greater than average, select order amount from orders. Okay, so that subquery will run all by itself. There's nothing contingent there, and that the subquery needs from the outer query. Okay, but you'll select all the items in the outer query when this condition is met. So when this is in, this end clause is looking for this. Okay, so the outer query needs the subquery to run, right? Otherwise, there's no condition for the end clause, nothing to run. But the subquery all by itself will run. Okay, this is a non-correlated subquery, and here's the result. Now, correlated subquery requires the. Let me get this right. Requires the place order is greater than the average order amount. It's correlated because it references the customer ID from the outer query. Yes, so we need the outer query to run. Otherwise, we have no customer ID, and then the subquery will not run too. Okay, so we have select one. So this is the top one from orders where that customer, and you can see an alias here. Orders is has an alias of O. Then that becomes the table name for this part of the query, right? So the reason to do this is it's just a shortcut. It saves you some typing. You don't have to type orders over and over and over, and you don't have to type customers over and over and over. Here's the alias for customers. C is the alias, right? And because that works, then we can use this alias down here, this C. All right, so we have our customers alias and our orders alias, and we run the correlated subquery and get this. So pretty cool. Okay, I have some more notes over here describing a little more detail about how that's running. Here is a cumulative total or running sum. So we create the table, insert into transactions. With these types of queries, this is pretty cool and very helpful. You would have an over condition and order by. So the order by is going ahead and telling us that we have to order all of these orders by transaction date. And that makes sense. If we want to see a running sum of everything, we have to order this by date because we want to see day number 1, 2, 3, 4, and 5. If it don't order by, then the running sum is going to be meaningless because we don't know how it's doing the sum, right? It could be arbitrary. It could be day 2 could come first, and day 4 could come second, and day 1 could come third, right? A table all by itself has no order, but when you order by, then you introduce an order, some order logic into the SQL code here. Okay, so order by transaction date. I believe this is it this descending or ascending by default? I forgot. You can use ASC or DESC and then get it right. I forgot what the default is. Might be descending as running sum from sales. So you're summing everything over, and this is the condition, right? We have to have an order by, or it's going to be meaningless. And here's your running sum. So we have 100, 250, 451, 751, 50, right? So you can see how it's cumulative and it's increasing. So a couple other techniques or functions. These are called Windows functions I'd like to introduce you to is row number, rank, and these dense rank. These functions are Windows functions assign a row number, a ranking, and dense ranking based on whatever logic you pick, salary and descending order, right? That's what we're looking at. Row number assigns a row to each, so we have 1, 2, 3, 4, 5. Otherwise, there's no row counting in SQL by default. A rank assigns a rank to each unique salary, and where there's ties, the rank, the same rank is assigned. So we could have a rank of 1 showing up multiple times if they're shown up as ties. A dense rank is basically similar to a rank, but there will be gaps between the ranks for tied values. So you'll just see 1 if there's multiple 1s ranked, right? And then it skips to 4 or 5 or 6 or whatever the next number would be after the ties are broken, right? But rank would have 1 for all the ties, and 2 would be the next highest rank, right? You wouldn't have any gaps, but the next highest rank with the dense rank could be 3, 4, 5. You don't know what that's going to be until you hit the non-tiebreaker, right? Non-tiebreaker is gonna determine that. So here's a quick example of these, and these Windows functions are very popular. I use these all the time. So let's create a table, insert some data: Alice, Bob, Charlie, David, Eve, and then salaries for each one. Then we will go ahead and do the salary row number. That's the Windows value function, order by salary in descending order, right? These are descending, the ASC is ascending. So we have row number, rank, and dense rank, and we can see what the differences are. So we have row number, that's pretty intuitive, 1, 2, 3, 4, 5. Rank, 1, 2, 3, 4, 5, and then dense rank, 1, 2, 3, 1, 2, 2, 3, 4, because the salaries are the same. For Eve and Bob, they have the same salary. So dense rank is not leaving any gaps. If this was a rank, oh yeah, so we can see the difference here. So rank goes 1, 2, 2, 4, 5. The 3 is skipped because Bob and Eve have the same salary. And dense rank is including the 3. It's not skipping any. So we have 1, 2, 2, 3, and 4. So it really depends on your use case and what the overall ask is, which one you'll pick, but I can make arguments for both. So let's move on to advanced SQL. That covers the basic and the intermediate SQL. Let's move on to advanced now. Okay, hierarchical SQL is great for finding parent-child relationships in data, right? A lot of times a parent could have several children. Certainly in an office or in some type of business, a manager can have several employees, right? The manager would be sort of the parent, and the employees would be the children of that manager, right? So let's do the insert like we saw before. Select employees. We're going to use the alias E. Employees as E and managers as M. So here's the alias for employees. Employees are E. And again, it just saves us a lot of typing. We don't have to type out employees every single time. The convention is to use 1 or 2 or maybe 3 characters to represent the alias of that table, just so you don't have to type it out all over again. When we use a left join, we're showing the CEO roles wouldn't be displayed because the CEO is the top manager as the manager ID, but you can see all the managers and the salaries, and the hierarchy is higher than the boss. No, the CEO is the top, and manager A and manager B are not higher than the boss, but employee 1 is, and then employee A2, B1, B2 is not. Okay, so gaps and islands is another problem that you might encounter. This is very interesting and somewhat challenging too, but it's a pretty fascinating problem, especially when dealing with sequential or time series data. This type of logic helps you find gaps in the data, right? If there's missing dates and your time series data, or anything that's missing would be a gap, and an island would be something that's that's included, right? It's not missing. So let's take a quick look at this. We are again creating a table and then inserting into. So we have the log events, log in, and then the date and the time. And we're going to select the event ID, event type, row number. We just saw an example of that in the intermediate table. Partition by is kind of doing a group by, but you're showing all of the petitions and you're not rolling up everything. So partition by is sort of a group by, but you're not rolling it up into some type of aggregation. When you're doing a sum, account, an average, min, mean, max, mode, standard deviation, right? You're grouping by. In those cases, you're rolling up everything and doing the aggregation. The partition by is grouping by, but not doing the aggregation. So we have the row number over partition by, time event, partition by user ID, and event order by time events. Okay, so the partition by is doing the group by, and the order by is giving us the descending order. I believe the descending is the default. If you're not sure, just write DESC after timestamp and DESC over here. If you want ascending, then it would be ASC, right? So we select the min max from the ranked events table, and we get this result. Okay, so that's gaps and islands. You can see if there's anything missing in your time series data, gaps and islands is a great way to help you find those gaps in there, right? Okay, here's a scenario where the data is stacked vertically with lots of rows and only a couple columns, and we want to go ahead and I think this is an example of a pivot. Okay, so we have product A and B and some months and some sales amounts. Yes, it's pivot, so we're going to do a select from. Okay, down here is the subquery. Whoops. So there's select from. And the alias is source table. Okay, and we are going to go ahead and pivot that. You need some type of aggregation. Min, max, count, sum. These are the popular ones. Sales amount. And you have to do sort of a loop here for a month in. For a month in January, February, March, and we're going to go ahead and pivot that data so it goes horizontally in columns, not vertically. So this is pivoted, and you spread this out into multiple columns from 3 into 4 columns, right? Product A, product B, and then all the details under those months. But you can also do an unpivot, right? If you had a lot of columns and you want to stack this, you can do the opposite of a pivot. Here's your subquery, select from. Here is the source table, right? That is the alias source table. And on pivot, again, sales amount for a month in January, February, March, because this is spread out. Now this table is rendered differently and we want to stack this. So an unpivot will get us back to the initial view that we saw before. So SQL is very useful for transforming data into all different kinds of views, pivoting, unpivoting, certainly aggregation, some mean, max, min, counts, things like this, right? So CTE is a common table expression. This is a way to introduce some sort of recursion into your code, right? So if you have to do something over and over, like a loop, you can use the CTE process to go ahead and do that for you. So certainly if you're trying to find relationships in hierarchical data, this is very helpful. If you had to create a whole bunch of dates in within a year or within several years, you can have a start date and end date and use the CTE to build out all the dates for you and to insert data into a table that way. So there's many applications for CTEs, right? So we're going to go ahead and insert into. Pretty standard stuff here. Here's the CTE, common table expression, to calculate total salary. So anything with double hyphens in front of it is just a quote. We'll start the CTE with the with statement, with department as select, and then you have department ID, sum, salary, group by. Then you have to go back and reference the CTE. So once the with is running, you do select e.employees, right? There's the alias again, and DTS, department total salary. Okay, when we run this, we have the recursion logic showing us employees, employee name, salary, and total salary. Okay, so recursive common table expressions are used to perform recursion, which is some type of looping. process, such as transversing hierarchical data structures, employees and managers, things like this. If you're building a table and you need a lot of dates populated, you don't have to type out all the dates. You can create a CTE to build the dates dynamically for you to populate data according to whatever logic you need to be done for you. So think of the CTE as a loop. Okay, here's another example with recursive CTEs. We can look at subordinates for each manager. We have the with statement again. They always start with the with and the as. Okay, so these are sort of the two anchors. And then this is the name of the CTE, recursive subordinate CTE. Okay, and that is what we join down here. After we do our selects, we have our aliases, we have employees. The alias is E, join, recursive CTE. Okay, so not that, sorry. So the mouse is not behaving. Now it is. So we have our recursive CTE that we reference as we name it, after we name it at the beginning. So we have the with, the name of the CTE. It could just be CTE if that's what you like. I like to make these have a name that has some kind of meaning or purpose. So if you're looking at this after a few months, it should still make sense to you. If you just call it CTE and you don't give it a definitive name, then you might not know what it's doing. Like the logic could work fine. It doesn't matter to SQL, but for any person that reads this, if you call the CTE just CTE, it might not make a whole lot of sense to some people, right? So we want to try to make that meaningful and definitive, right? So we can use a couple other clauses. You'll see this from time to time, except and not in. So the in clause will get everything, as you can imagine, that's inside of that, matching that condition, except operates on the entire result set, return distinct rows. All right, not in filters out rows based on the specified value compared to a set or result of a subquery. Okay, and the difference could be nothing at all. These two could perform exactly the same, or they could perform slightly different. Usually, if there's nulls in the data set, you will see differences, right? So the except will show you distinct rows, and I believe the not in will show you the nulls, right? Anything that's null or not existing, I think the not in shows you that, or maybe it's vice versa, I forgot. But these two are pretty similar and will produce exactly the same results in a lot of cases, but they could give you different results, so just be aware of that, okay? Okay, here's an example of the except. Select all from except employees in the old table and employees in the new table. So this is an easy way to look at differences between two tables, right? To see if some records don't match, to see if most of the records match, but we have some non-matches too. Okay, so okay, and then here's another example of the not in, so you can see the differences between the except and the not in, and in this case, they return exactly the same, right? That's what I said. So a lot of times the not in and the except could be the same, but there could be differences too, right? So you just have to be aware of that, okay? Dynamic SQL is great if you're trying to create SQL at runtime, right? So you can create dates dynamically, any kind of fields dynamically, do parsing, addition, subtraction, counting dynamically, right? So the SQL will actually create SQL as you run the code. So you don't have to predefine the SQL. It can be created dynamically as you write that. Okay, let's try to see an example. Here's a perfect example. Okay, so let me go up a little bit. Create procedure. And I'm starting with a start date and an end date. So this is a dynamic SQL. You have an ampersand, and then you name your variable start date, end date as begin, and you declare the SQL. Set the dynamic SQL. The ampersand means dynamic SQL equals n, and select event ID, event name, event date, and events where event date is between the start and the end. Okay, so you can dynamically pass in these dates. We have 4/1/2023 to 6/30/2023. So this SQL will go ahead and use a start date and an end date, and anything between these two dates will be returned. So this is a pretty cool way of making things dynamic. If you wanted to say, select everything for the last 30 days, for the last 90 days, for the last 1 year, or something like that, you can do that dynamically using dynamic SQL. So that's kind of cool. This last example here is something I did for a job I had about a year ago. This is kind of a custom example. I don't think we really need to get into it, but I'll show you. Like, SQL is pretty powerful. So in this example, I'm looking at some conditions. I want to see all the records that have 7 a.m. to 11 p.m. Monday to Friday, or 7 a.m. to 11 p.m. Saturday or Sunday, or 11 p.m. to 7 a.m., which is overnight, any day of the week. Okay, so the first requirement is going to give me a 5 by 16, so Monday through Friday, 16 hours. The second one is a 2 by 16, that's 7 a.m. to 11 p.m., 16 hours, 2 days a week, Saturday and Sunday. And then any other date, that's a 7 by 8, that's overnight, 7 days a week, 8 hours. Pretty much people are sleeping 7 a.m. to, 11 p.m. to 7 a.m. So I'm going to go ahead, create the start date using a dynamic SQL, insert a counter, integer equals 1. So it's going to go one by one, insert all these records between these two dates, basically getting, let me see here, January 1, 2022 to 12/31/23. So all of 2022, all of 2023, it's going to insert 365 times 2 number of dates. So what's 367? 25, 730, so 730 dates. I'm not sure if this is a leap year or not. That's going to be inserted into these tables. Okay, so I'm using dynamic SQL. And then I'm going to use the when clause like I showed you earlier. And I am going to look for the event date and time between 7 a.m. and 10 p.m., right? That's 22. And then 11 to, or 23, that's 2300 hours to 6 a.m., less than or equal to 6 a.m., and then the in between is Saturdays and Sundays, right? 7 to 22, and give me Saturdays and Sundays for 16 hours, and that's exactly what it does. So we have the date, the event value, and then the time category 7 by 8, right? That's overnight, 7 days a week. 2 by 16, that is the weekends for 16 hours, and then any 5 by 16 would be Monday through Friday. Okay, now here's a slightly different scenario. Again, very custom. I don't think you'll ever see this in your career, but it's pretty powerful what SQL can do. So I'm just showing you this as an example here. Something I did, but it is a very specific type of query. I don't think you'll necessarily need to use it, but it does take advantage of a lot of these functions that we saw before, or clauses, right? Average, case when, date part, between 2 and 6, and then 7 to the 22, and then 722, that is Saturday and Sunday, or Sunday and Saturday. So Sunday is 1, Monday, Tuesday, Wednesday, Thursday, Friday is 2 through 6, and then Saturday is 7. That's how we get that. Okay, so we're using the and clause, between clause, and greater than 23. That's 2300 hours or less than or equal to 6 a.m. And what do we have when we take a look? We have the event date, and then we have the 5 by 16, 2 by 16, and 7 by 8 for the weekend. So that's it, guys. Pretty cool stuff. That's SQL, beginner, intermediate, and advanced. That covers a lot of scenarios. Now, you might encounter some things that we didn't discuss here that will probably happen inevitably, but these are the most common types of things that you're going to see again and again. So that's it. I think, you know, if you're a SQL expert, you'll probably fast forward through a lot of this. If you're SQL curious or just getting started with this stuff, or kind of okay, but not too much up to speed, so a little wet behind the ears, that's fine. Just practice. You know, practice makes perfect. Try and try again, and you will succeed. So hopefully I showed you a couple new tricks or techniques, or gave you a couple tips for your tools and your toolbox. That's it. I love to learn new things every day. Hopefully I was able to teach you a couple new things today. And that is pretty much it. Wrapping up. Thanks for your time today, everybody, and have a wonderful rest of your day. Goodbye.